So chapter 3, state functions. Okay, let's get started here. We've got U is what plus what? Shelby, what's U? Our internal energy is typically what plus what?
Q plus W.
Q plus W. Okay, so that means it's infinitesimal change in internal energy would be dQ plus dW. But still, a differential is still just a change. I mean, you can make it a big change and say delta U, but we don't write delta Q or delta W. We still write Q plus W. I don't know if you're getting used to doing that or not. What's the reason for this? It's state functions. State functions only depend on what? Final and initial, like change in volume. Final and initial. It doesn't matter how you get to that final volume. The path doesn't matter. Just like internal energy, it's a state function. The path doesn't matter. But Q and W, they depend big time on the path, on how you get there, right? Work, heat, those are not state functions. Those are definitely path dependent. So it's kind of odd, I think, that you can get a state function by adding together two non-state functions, but that's how life is. Okay, so instead of looking at the functions, let's look at the differentials. So exact differential is just depends on the initial and the final state. That's the best definition of exact. The path doesn't matter. It doesn't matter how you got there. It's all depends on is the initial and the final state. That's not true of Q, right? If you want to get Q, it's path dependent, so it would be inexact, right? An inexact differential. Okay, so if you want to get Q, so you get numbers for both. It's just that one only depends on the initial and the final state. Okay, and we don't talk about states really when you say heat and work. It's just because they're not state functions. And then we talked about this in our concept review, right? This was called the what derivative? Like you say f is a function of x, y, then they call it they call it the total derivative. All right, that's how it's defined. And then this function is exact, so it only depends on the final and initial state if all this held true, and we spent a bunch of time with some functions and seeing what's exact and what's inexact. Okay. Changes in internal energy. So you see what this path is just, this plot's just trying to say, here's our final state, our initial state. Well, you get the same delta U regardless of the path that you take. So it's a state function. Okay. Changes in internal energy. So change in internal energy that arise from changes in temperature and volume are related by this. Okay, let's take a closer look at it. Right? Like this internal pressure. And one thing that I think we need to get used to, and it's not going to be very easy. First, take a look at it and what it means. This is how the internal energy changes with respect to volume. And what's the state constant? Temp. So that makes sense then that it's always 0 for a perfect gas. Okay. But don't forget that these guys are really slopes, right? It's that if you knew the change in internal energy, you knew the change in volume, just divide the two, and you're going to have this, right? So it's funky that you have an equation here. It doesn't look like this is an equation, to plug in and get answers, but it is. If you want to get the internal pressure, and it's in the homework, and it's going to look confusing, but it's not. If you know what delta U is, you know what delta V is, Divide the two, you have the internal pressure. That works for all partial derivative relationships. It works for all of them. Now, when it gets ugly, and also, so in a homework question that involves a partial derivative expression like this or whatever, when they want this, awesome, because that means they're going to give you delta U and delta V. All you do is just plug them in and calculate the slope. The problem is when they want one of these. What's the change in internal energy? What's the volume? Then you have to integrate, because the only way to get rid of that differential is to integrate. And that's when things get ugly, and we'll be doing some of those in the homework. Hopefully we'll hit those first. Okay, so just realize that's coming up. Now, that's, yeah, so this internal pressure is 0 for perfect gases. But for real gases, you look over here. And it's internal energy, you know, it's not 0. So what they're trying to say is, let's see, what is that? That's a volume. So volume is going this way. So in this plot here, if V final minus V initial, this part's always positive, right? Because if volume is getting bigger, volume is increasing in this, whatever this process is of this gas. Is that expansion or compression?
Expansion.
It's expansion. Good. So this is expansion we're talking about, going that way. Right? So that means my delta V is what, Gloriana?
Is
Positive.
delta V?
Yeah,
Positive.
positive. Yeah, delta V is going to be greater than 0. So if delta V is greater than 0, but look at this slope, right? This slope is supposed to be the slope of this plot, this top part here, where it says repulsions are dominant. The slope is positive or negative, Kevin?
Negative.
It's negative. Well, if it's negative, that means that, and delta V has to be positive, that means delta U must be negative, must be less than 0 when repulsions are dominant. So let's see if that makes sense to you. You have all these molecules, right? And the dominant intermolecular force is repulsion. So do these molecules want to get separated in the first place?
Yes.
Yeah. So you're just letting them. So the internal energy is dropping like a rock because you're letting them do what they want to do. So in that sense, and it's kind of hard to use the word want, but it's what nature wants to happen or tends to happen. So the internal energy drops with expansion when repulsions are dominant. But look when attractions are dominant. Right? Again, you have delta V, it's still expansion, so delta V is greater than 0. But now my delta U is
Less than 0. Oh, yeah, good. Yeah.
greater than 0 because the slope is what, Kelly?
Positive.
Slope is, right? For now we're talking about attractions are dominant. The slope is always going up. So the slope is positive. So if the slope is positive, this has to be a positive number. Well, this guy, right, it's expanding, so that's positive. This has to be positive too then. So delta U is greater than 0. Make sense? So attractions are dominant. Well, now you're trying to make them farther apart. You're increasing the internal, it's kind of odd. It's harder to explain. This one's more conceptually difficult, but you're not doing what nature wants. You're trying to spread these things farther apart when they want to be together. You're giving them more space, more volume. So you're working, internal energy is going to go up. Kind of like raising the potential energy, kind of like. Expansion coefficient. Let's see. Okay. If alpha, let's see if we're following this here. If, let's say alpha was huge. So all these gases, they have all these different values. They're real gases. They're all tabulated, right? And then you can plug in the numbers and get this stuff. But if this was large, what they're trying to get out of this is, well, what's the big deal if this is large? We're going to expand this and the pressure has to stay constant though. And if you have a really small change in temperature, that's going to, well, it doesn't need to, if this is, it's going to expand a lot with a really small change in temperature, is what I'm trying to say, because alpha is huge. So if the temperature just goes up a little bit, just small changes in temperature are going to result in a huge change in volume in order to keep the pressure constant. So I don't know if that's much insight or not, but that's kind of what it's trying to say. If enthalpy, if something is adiabatic, that means Q was equal to 0. Does that mean delta H is 0? No. No, not necessarily. I think it would if it's an ideal gas. I think. But it's, you know, you're playing a dangerous game there. So just because Q is 0, it doesn't mean it's isoenthalpic. Would be the word, I guess. Okay. Isothermal compressibility. Where'd that equation go? Oh, we lost it. It's kind of down there. So I think we're playing around with this. I think what we should do is V is nRT all over P, right? So if I took the partial of V with respect to P, I would get, let's make it look better. What would it be? Yeah, with respect to P.
nRT over P squared.
Yeah, good. Pull out that nRT, right? Because don't worry about it. It's not, you're taking the derivative with respect to P. And you're already being lazy. We should have a little subscript saying constant N and constant T. But take the derivative with respect to P. So it's going to be a -1 comes out front, and P becomes a -2. So what this really is turning into here, but V is nRT over P. So I could put P over nRT here just for that V. And then I've got a negative nRT. This is kind of a mess. But what I'm trying to get at is, see how you end up with just 1 over P if you play around with it. I wouldn't worry about this. What I'm trying to get at is that if you want to compress something, and it's a lot easier to compress something when the pressure is really low, because if P is small, you get a big kappa, and it kind of makes sense. If the pressure is low, it's a lot easier to compress. So it's kind of silly. But
I think I know how it cancels out. You sub in nRT for dV, or for the partial of V.
yeah, so this part is that.
Or now if you leave that as 1 over V, and then you multiply it through, you'll have V times P, and that's equal to nRT. So you can cancel it off that way. That's how you cancel off the nRTs.
Well, what I did is 1 over V is the same as P over nRT, and the partial of V with respect to P is this mess. So the nRTs will cancel.
I thought you were saying it didn't cancel out.
Oh yeah, it does. Yeah, and then one of the P's cancels, and you end up with 1 over P. So it's kind of a mess. Don't worry about doing that. The point is just that you end up with the idea that low pressures have a higher isothermal compressibility, and well, you kind of already know that. It's kind of common sense, but. So I like this one. I think this one's interesting. Here you're getting into how gases respond as you change the pressure. Do they cool down or do they warm up? Right? So you're letting something expand. If you're letting a gas shoot through a nozzle, right? The delta P would be positive or negative?
Negative?
Yeah, because P final is going to be really small. P initial is huge, right? So let's expansion. Delta P is less than 0. So if it's expanding and delta T is, let's say it warms up. If it warms up, this gas heats up as it expands. Delta T would be positive. So then my Joule-Thomson coefficient that you can look up in a table, that is going to be negative or positive?
Negative.
It's going to be negative, right? So that's what they're trying to say down here. Like, oh, it's hard to read this. But some gases will have negative Joule-Thomson coefficients. If you expand and delta P is, so expansion, delta P is less than 0, but the thing actually gets colder, right? So the final temperature is lower than the initial temperature, then my Joule-Thomson coefficient would be positive. Okay. So an example of something that has a positive Joule-Thomson coefficient is carbon dioxide. Okay. And what I was trying to play around with is, in fact, that's how they make dry ice. What's dry ice? So it's ice that's not wet. What the heck? How can you get ice that melts and stays dry? You're talking about frozen CO2. And the easiest way to make it is to have a nozzle and have the CO2 shoot out of that nozzle. Right? Like we have a great big cylinder over there, and it shoots out of this nozzle into this, essentially a bag. And you end up, and it freezes. The CO2 expands so fast from such a high pressure that it freezes instantly, and you get dry ice. And it's dry because, yeah, it's super cold, but then it just sublimes. It goes right to CO2 gas. So it's kind of nice for picnics and things. And it's not so nice, easy to find though. Okay, but you can drop it in water. You can play around with dry ice. It's a lot of fun. But one thing that one of the labs that we were, if I can still get it working, we'll do it. But this really starts in Wichita, Kansas, with Tornado Alley. It's horrible. You would think they would understand how tornadoes work, but they really don't. So what's going on, there was this guy who, somewhere in Kansas, and he went under the underpass, and then as the tornado went directly over him, first he felt hot air, then he felt cold air, then he felt hot again. So what they believe, they don't even know how tornadoes are going on here, how they work, but what they believe is going on here is that there's an angular momentum transfer between the molecules in the center going to the outside. So you end up with this cold region. So that's kind of what's behind this Rank-Hilsch tube. And they use these in manufacturing. And it does something that I've always thought of as thermodynamically impossible. For example, you have this room, and it's got a distribution of speeds, right, of all the gas molecules. Some are moving fast, some are moving slow. It's called the what distribution? Starts with a B. Boltzmann distribution, right? So you have this average speed. But the point is that they're evenly distributed out here, right? Not population-wise, but they're evenly randomly mixed. So it would be impossible to get all the hot molecules over here and all the cold ones over there. Don't you think? A Rank-Hilsch tube. You hook it up, and you need a hot spot on an assembly line. You need a cold spot on an assembly line. Just imagine all the refrigeration that it would require, or all the heating elements. No, use a Rank-Hilsch tube. What happens is you hook up your gas to this end, you get hot air out one end and cold air out the other. And when I first heard about this, I thought, this is impossible. No, they sell these things, so I went out and bought one. And then we did a research project and we built some, so that's what your lab is on. But the point is, the reason why I'm telling you all this is that's how they believe this thing works. There's a momentum transfer. You get this tunnel action going on. The article that we wrote explains a lot better, but you end up getting momentum transfer between the inner and the outer currents, wind currents in here that are going on. They're spinning. And so you end up getting the stuff that absorbed the angular momentum, hot, and the stuff that lost it, cold. So it's really kind of the inner and the outer shell of, like the tornado. So it's some insight in the tornado. It's pretty interesting, but I don't know what the hell. I think I dropped it and broke it. So it kind of sucks. But that's kind of what's going on there. Okay. Yeah. that's about it. So there's some relations here, and I say we just go ahead and jump into the homework. But I want to jump to 310 first, because it's a common problem here. 310, then I want to jump down to 313 and do these first. So it wants the Joule-Thomson coefficient. So you're going and hunting for it, or use that equation sheet, right? It'd be faster just to use the equation sheet. But now, notice if you flip over to the equation sheet, this is something that does bite people in the behind. You got to know what the symbol is for the Joule-Thomson coefficient. It's the mu with a little t on it. If you don't know that, the equation sheet's not going to do you any good. All right, so that's just something you got to know. Okay. Well, that's isothermal. Whoop. Here. Okay. So any ideas?
Delta T, yeah, delta T over delta P.
Yeah, it's just delta T over delta P. It's that calculating the slope. You know how the temperature changed, you know how the pressure changed. And it's good.
So that's
all it is.
That H is like constant enthalpy, right?
Constant enthalpy. There's your temperature change, and calculate your pressure change.
We don't have to worry about units on this?
Now, what did I do for T? Well, I think what you do is just keep your units in there, right? Whatever you had, okay. This is going to end up being kelvins per atmosphere. Fine, just leave it in that, right? Now, if they wanted something else, just don't give the number, give the units. And then, you know, if the units are different in the back of the book, well, you can always convert, see if you did it right, but that's all this is, okay? Let's jump to 313. Does that make sense? Let's jump to 313. Just divide the delta T over the delta P. Delta T is what? Negative 22 divided by, what's the change in pressure? 1 minus 32. Right, that would be a negative 31. Right. And just get your answer. For 13. Okay, isothermal compressibility. Let's jump down to 13. So isothermal compressibility was that a kappa T expression. Okay, so what I'm trying to really drive at here is see what the question's asking for. Isothermal compressibility, so I just slap that equation down. Done. And then look what it's after. It's after the pressure. The pressure is one of the differentials. So what's the solution? You're going to have to integrate. Okay? So if you're going to get stuck integrating, we're going to figure out how we're going to do this. First, I would rearrange it for dp. Right? I would bring the dp up to the top, bring the kappa t down to the bottom. Here at kappa. Right? Something like this. Oh, I just changed it to a, because I'm getting ready to integrate. So that's why I changed the partials to little d's. Okay, so when I integrate here, I'm gonna have to hang on here. First, I need my pi, and I need a pi and a pf. I got to put those in, my limits, and then my integral on my volume. Now, is this kappa t isothermal compressibility? Is that something you just get from a table?
I think so.
Yeah, it is. Yes, it is. It's something you get from a table. So that means, is that going to be a constant? Yeah, so it's something you could pull out of an integral. So I'm going to pull that out. Because I have this integral that I have, right? V initial and V final. So I'm going to pull that 1 over kappa t out. I can pull out the negative sign, too. Make it easier. Can I pull out the V? No, because it's dV, right? You better not do that. Okay? You better not do that. So this really doesn't look that bad because they're after, calculate the pressure that must be applied. So they're after PI or PF?
PF, right?
Are they after PF? You agree with Eric?
Or no,
Kevin, which P are they after? Yeah, it's PF. Because what's PI?
the pressure that it already was at?
Yeah, what pressure was it already at? I have 1 atmosphere. Where did I get 1 atmosphere?
Standard states or something?
Maybe. Who the hell? How do I know that's 1 atmosphere? Psh, I guess I should have said that in the question. Anyway, somehow I've figured out, I think it's the only way to solve it. I said this guy is 1 ATM, and this is the one I want to solve for. So, I mean, these integrals aren't very hard at all. The hard part, I think, is figuring out these limits. Okay? And, oh, they even told us what kappa t is. Here's, oh, okay, good. There's my, it still doesn't help. I don't know how it's 1 atmosphere. 293. Anyway, there's my kappa t. So I can always assume that. I'd tell you. If this was on the exam, I'd tell you. The initial pressure is from, if you want to compress it, from this pressure, what's the pressure that needs to be applied? Okay. I guess you're supposed to imagine you're on a bench and you want to start applying pressure. Well, you're initially at 1 atmosphere. I guess you're supposed to assume that. I don't know. Okay, but the point is you want to increase the density by 0.08%. So this is a little tricky. If this is how I did it. Density initial let me just give you the answer. See if you can see how I did it. Does this make sense? That I subtracted that 0.08% from 100.
Yeah. That
the initial density is going to be a little bit less than the final density. Okay, because I'm compressing it, right, by 0.08%. Okay, so what I'm doing, why I'm doing this is the only way I could conceptually figure out how to get these limits. Maybe someone will come up with a better way, but we'll just run through this one first. Density is m over v. Now I'm talking about initial and final, so I have, all right, m over vi. I'm not adding or subtracting any mass. So if you put it on the balance, that's not going to change. So that's why I didn't put a little I on the M. Okay. So my M's are going to end up canceling. All right. So how do you solve for this thing? Bring the VF up to the top on the other side, the VI, right? Do you see the math here? So the VF would be 99.92% VI. But percents don't, how do you get rid of a percent? You move the decimal place 2 times. Now, is there a way for you to jump from this density by 0.08% and just conceptually jump down there? My brain couldn't do it. Because since they said density, I had to plug in, I had to start there.
I guess if you just remember
Yeah.
VF equals the opposite of the percent VI in decimal form.
I don't know, it's hard. So, but to me, that's what makes this problem really tough, and that's why we're doing it. So now you know what the limits are. You plug them in, right? So you do the whole integral, right? And then at the end, you can plug in this relationship and get rid of your v's. And what's the? I don't want to do the whole thing, but you get the idea, right? Good. Yeah, 1 over v is going to be ln. Then you have the limits from vi to vf, right? And vf is 0.992 vi. So you could just substitute in vf 0.9992 vi, right? And then you'd have the natural log of vf minus the natural log of vi. But remember, subtract natural log, that's the same as dividing them. So that's the trick, really. To me, that's really the trick. You'll have the natural log of v evaluated from vi to 0.9992 vi. Right? So that's the natural log of 1 minus the other one. So 0.9992 vi all over vi. And your vi's cancel. See that game? That's how you get rid of them. And on the other side, it's just, on the p side, it's just going to be what when you do that integral?
Just p, or just p, right? Or, no.
Yeah, p evaluated from pi to pf, so you end up with pf minus pi. Okay, and your whole goal is to solve for pf in that mess. So that's an ugly question. Okay, so I wanted to just give you a skeleton, well, a little more than a skeleton, right, to get that one going. So what the heck happened here? By direct differentiation. So let's go back up to the top. Number 6. So are you comfortable with your game plan for the other two? Melissa, you comfortable with this? So, okay. So if you have a question, ask Melissa. 3.6. Okay, by direct differentiation.
So it's not supposed to say differently.
So start with these. You just haven't had much practice in, and that's okay. So H equals U plus PV. And all you want to do is play around with this thing until you get just left with this kind of stuff. So let's take the partial of H with respect to what, probably? On both sides? Well, you could, if you did P, you'd end up with partial H with respect to P. Let's do it with respect to U. Because see the goal? The goal is these two. So I'd take it with respect to U also. So what did I do here? Oh, we didn't. I'm already getting lazy. It's not enough. It's with respect to what that little guy is going to be important. Constant pressure. That's where I was like, how the hell did I do that? Okay, now it makes more sense. So on this side, I'll have partial of H with respect to U at constant pressure. Right? So I've already nailed one of these. So I'm on the right track. So if I take the partial of U with respect at constant pressure, the partial with respect to U, of U, you just get 1. So that's just going to be 1 plus. Now, P is constant, so how would you write this next part? Plus P there. That's it. Right? Okay. Now, do you recognize? So this guy's, they want a relation between these two. Doesn't matter where they're at. We're close. Man, it'd just be nice if we could do what to this? Remember the concept preview. Just flip it. Now, we didn't have a little, what do we call these corollaries? We didn't have one that said just flip it. It was called the, not the permuter, but the inverter, right? So look at the concept preview and you just use the inverter and you're done. Okay. What's in you? I think it's in those pages in the appendix, right? Because you just copied them from the book. Okay. Let's see if we can get 3.8. I remember that. Okay.
Wouldn't that first one be 0?
Yes. Why?
Because perfect gases.
Yeah.
Energy doesn't change with volume.
Yeah. So as ugly as these get, don't forget the fundamentals, right? Because it's a perfect gas. So T is constant. Doesn't matter what ugly thing they give you. Okay. So do you see this thing here? They're trying to say that, well, that R, that should be a capital R, right? Right. They're trying to say that this delta U is 3/2 nRT. Well,
Don't they say that because like those two terms add up to B delta U?
so what we're supposed to do is realize H is U. This is what they want you to play around with. H is U plus PV. Well, you're supposed to plug in and they want you to end up taking the partial with respect to v on both sides. This is what the part they want to know. So you'll have the partial of h with respect to v at constant t, but then you got to take the partial with respect to v at constant t of this mess of u plus pv. And all they really want you to do is, it's kind of stupid. So I was wondering what the hell I did here. That's why I don't really like this chapter 3, because it's just weird stuff. So what the heck are you going to use it for? Like u is the 3/2 nRT. That's what they said. But PV is also equal to nRT. So you write plus nRT. But 3/2 nRT plus 5, it doesn't really matter what it equals. You're taking the derivative with respect to v. There's no v. So it's 0. So this guy is 0. They're both 0. So it's kind of silly.
Can you say that one more time?
So what they want you to do is they want you to find the partial of h with respect to v at constant t. The only way to do that, here's your h function. So we need to find the partial with respect to v at constant t on both sides of this.
Oh, yeah, I see.
So here's this side. Well, that's what we want. That's what we want to solve for. So for u, you plug in 3/2 nRT. For PV, you plug in nRT. And then you take the derivative with respect to v. And there's no v there, so you just say 0. You get what? 5/2 nRT. Well, there's no v. So yeah, I'm glad this chapter is only one day. What's that? We're supposed to do all of them? I think it was 3.8. Yeah, 3.9. Okay. Start with 3.9. We have about, maybe we can get this guy knocked out here. Alpha is defined in equation 7. Oh, we already know what they are. We can just write them down in our notes. All right, alpha is, instead of using that cheat sheet, let's copy off here. This is number 9. We want to show that this is true. This is what we're after, right? And remember what alpha is. Alpha was the 1/v partial of v with respect to t at constant p. And kappa was negative 1/v partial of v with respect to p constant t. So I'm just copying down from the notes. And they want you to show this. But start here. So they're saying that v is a function of t and p. So Melissa, how would I write dv then? The total derivative. Because that's what they said. They said starting from the expression for the total differential of dv in terms of t and p. So that's what I'm doing. V is a function of t and p. So dv would be partial of v with respect to t, p is constant, times d p, okay, plus, not d, partial, dp. Okay. So we have, we're getting close here. This is looking really close to that, isn't it? We just need to multiply it by 1 over v. So if we multiplied everything through by 1 over v, that would give us that. All right. I think that's what I did. Is that what I did? Oh no, I'm trying to get alpha and kt in here. So what I want to do is write it kind of like this. If I want to get an alpha in here, I have to multiply it times v. That's what I did. Right? Because v times alpha would be that. Right? Because I'm trying to get this set up so that I'm trying to end up here. So I need to get alpha and kt in this ugly mess. So I did that. That's how I got my alpha in. Okay. And how do I get my kappa in here? How would I get that in there? Multiply by a negative v. Do you see that? Because negative v times kappa t would be this. So I bless you. Okay. Now the next trick in doing this mess is they want the partial p with respect to t at constant v. So p with respect to t. If I went through, what did I do next? Oh, that's what I did. Okay, so what I did then is I went through on both sides. Did this to both sides. This whole thing goes in there. Because you see what's going to happen here. They're trying to say that v is constant. Well, right away, this side's going to be 0. Because v is constant. And all I have is v here. So that first part's going to be 0 on you. And then I've got, I better write this in or it's going to be really ugly. It's going to be hard to see. V alpha dt is v kappa t dp. So when I pull my partial derivative through here, v is constant, so it goes straight through. Okay, my alpha, well, that's just constant. I mean, alpha's alpha. So I end up with dt over dt. That's going to be my 1. Did I lose you? Because first the v goes straight through that partial derivative, and then the alpha goes straight through too. It's just, think of it as a number from the table. Then you end up with dt over dt. That's just 1. Okay. And then you do the same for the next part. Minus pulls straight through. The v constant pulls straight through. The kappa t pulls straight through. But the p is going to stay there. This is a really hard one. Am I getting close? What was that? Yeah, there it is. So that's why that's going to be a v. That's why I did the partial with respect to t at constant v, because that's what we were after. That's what I missed. I couldn't see what I did. Because I was after this with respect to t at constant v. That's why we did this step right here, because you're after that partial t with respect to p at constant v. That's tricky. So you just rearrange, and then you'll have this, and you're done. Just solve for this guy. Oh, we're out of time. So that's the type of problems that you've got to mess with in Chapter 3. So give it a shot. The exam isn't going to be worth as many points as the other exam.